So you have all the rules, you're ready to go do the homework. Before I send you off, I want to talk about some big picture stuff about the difference between definite and indefinite integrals. So here's one topic. If I write the integral from 1 to 2 of x squared dx, a definite integral, and I write the integral of x squared dx, an indefinite integral. A few things about the differences between them. This one, the answer is a number. We could find that number. This one, the answer is, you want to say it's a function of x, but it's not a function, it's actually infinitely many functions of x. The fact that our answer is a number here means that the letter x doesn't matter. The answer is, I can't do the answer in my head. The answer is some number, and that number is the same no matter what your choice of x is. So the integral from 1 to 2 of x squared dx is the same as the integral from 1 to 2 of t squared dt, is the same as the integral from 1 to 2 of u squared du. The choice of letter doesn't matter. In these situations, we say that x or t or u is a dummy variable. It's a variable whose choice doesn't actually matter outside of the expression that it's in. In this expression, the letter x is arbitrary. You could use any letter instead of x and you would have the same thing. With a weird exception that if x has a meaning outside of the integral, then the letter x, like the integral stops making sense. I can say let x equal 3. Now consider the integral from 1 to 2 of x squared dx. Wait, you want to integrate 3 squared with respect to 3? That doesn't make any sense. Like, you can't let 3 vary from 1 to 2. 3 is stuck at 3. Once x has a meaning outside of the integral, it breaks the whole thing. So this is part of what being a dummy variable is it needs to be a variable that has no outside meaning. Sometimes, if you tell a joke that has too many people in it, you might give the people names. Like 2 guys walk into a bar and the first guy says to the second guy something, something, something. And once there's too many guys or too many steps, you start giving them names. You say Al and Bob walk into a bar and Al says this and Bob says that and blah, blah, blah. And the joke works out fine. But if I told that joke as Barack Obama and David Letterman walk into a bar, well, wait a minute. Now, those words have meaning. This is a different joke now than giving them arbitrary names of hypothetical whatever. I'm giving them a hypothetical name. That's what a dummy variable is. And in this expression, the letter x needs to be a letter that doesn't have meaning outside of the integral. In an indefinite integral, the letter x is in the answer. The doing of the integral doesn't care about the letter, but the answer you get is different. The integral of x squared dx is 1/3 x cubed plus a constant, and the integral of t squared dt is 1/3 t cubed plus a constant. And these are different answers. And then an indefinite integral is the more normal circumstance where the letter is not a dummy variable. The letter matters to the answer. So that's one small point I wanted to make. Point number 2 out of 3 points is what's up with this dx. The dx only exists when the integral does. When I do the integral, the dx is gone. Because I did the integral symbol only exists when the dx is there, so the dx is gone. I've had students explain it to me that the dx becomes the plus c, and I don't think that's quite right, but thinking about it that way is fine, because the dx goes away when the plus c shows up. So if you want to remember it that way, that's a good way to remember what's going on. The answer has a plus c, only the question version has the dx. When the one goes away, the other shows up. That's a reasonable way of remembering what's going on. Okay, and now the last thing I want to point out is integrals and derivatives are different. A derivative, I mentioned this before, derivatives are algorithmic. The functions you can write down a formula for. If you hand me the natural log of the square root of 1 minus cosine of e to the minus 3x cubed over whatever, the rules of derivatives are closed. You can differentiate that. You can find the derivative and write down a formula for it. Right? Integrals are often not in the same way. As a quick example, the integral of e to the x squared is an easy example I know off the top of my head of a function that you can't do the integral of. Can't is a weird word here. When I say you can't do the thing does have an antiderivative, which means it has infinitely many antiderivatives by putting a plus c, but there isn't a closed form expression, by which I mean there isn't a simple formula for this function. And you could give a name to that function, but there would still be other integrals that you can't write down the antiderivative for with a simple closed form expression. As opposed to this thing, simple isn't the right word for it, but I can write down a formula for the derivative for it using the derivatives and the quotient rule and all whatever rules you need to use. You can write down a formula for the derivative. You often can't write down a formula for the antiderivative. The functions, one way of sort of pointing that out, what's the antiderivative of 1 over x? It's natural log absolute value x. If plus c. This integral is doable because natural log is one of the functions that we have given a name to in math that we're expected to, like it's got a button on the calculator. This function is also a function. It didn't rate as important enough to get a big name. If you take a stats class, you do get names for this. There are contexts where mathematicians want to give more names to more functions. But it's not in the canon of super important functions who have names to write down. So the integrals often exist, but it's hard to write down their names. What does this mean to you? The thing this means to you is that in this chapter, you're kind of learning a material similar to what you were learning for the gateway. On the gateway, you wanted to learn how to find a derivative. In this chapter, you want to learn how to find antiderivatives. But it's different. For the derivatives, you learn the rules and then you execute the rules. For integrals, you're going to be learning tricks and seeing if they work, and looking for better tricks, and increasing your proficiency with those tricks to get the hang of, this is the type of problem where this trick sometimes works. And trying things and seeing if they work. It's more like experimentation. It doesn't feel like math as you know it. Usually you think of math problems as things where you do the steps and you get to the answer. This is more like real math in the sense that I think of math, where you have a thing you want and you know some tricks and you see if the tricks work. Maybe you use the trick this way. How do you know which trick to use? Well, you practice. They won't get that much harder than they are in the homework, but this is a fundamentally different and harder thing than derivatives. Okay, if I don't add more homework problems, you can now do all the way through number 14. 15 is the first one that says to do a U substitution. I may add some more homework before I post this stuff, but stop this video, go do some homework problems. When you get to the U substitution stuff, come back here. Cool.